So, hello and welcome to another week of the NPTEL NOC 23MA14 uh, Algebra-II course offered by NPTEL. This is week 8. I am one of the PMRF TAs for this course. My name is Shubhajit Das, and I do hope that you are also attending Ajay Prajapati's sessions as well. So let's start right away. So this week you have been, what you have been doing this week was essentially a follow-up from the previous week. That is, you are learning about categories, functors, and this week you learned about natural transformations. So the questions for this week are based on all this stuff. Okay, so so without much delay, let us proceed. So let us read the first problem. So before we solve the problems, just a bit of some heuristic remark, rather I would say that so essentially, as I said previous week, the category theory is essentially about studying relationships between objects. Okay, instead of how the object looks from an internal point of view, you are interested more in what are the arrows from one object to another object. That is, how is one object related to another one, and so on. It is all about relationships. And whenever you study a new kind of mathematical object, you are always interested in asking this question: that is there a sensible notion of a map from one such object to another such object? And you can ask this about categories themselves, because categories are mathematical objects in their own right. And indeed there is the notion of a map from one category to another category that respects the category structure, and such maps, as you already know, are called functors. Okay, now once you understand what functors are, you can treat functors as mathematical objects in their own right, and you can again ask the same question, whether there is a natural notion of a map from one functor to another functor. And it turns out that indeed there is, and a map from one functor to another functor is what is known as a natural transformation from one functor to another functor. And just as you can consider a category, you can consider the category of all sets, you can consider the category of all groups, topological spaces, of metric spaces, of anything, of partially ordered sets, for instance, of rings, etc. You can also consider the category of all categories, right? So in a very there are certain logical issues here in this, but very crudely speaking, you can talk about the category of all categories. Or if we have some logical setup for the some base foundation, or some basic set theory on which we are basing our category theory, so we may be more precise. So let's say, is there a category which, we can talk about the category of all small categories, for instance, right? Now, this is a category. The objects in this category are all categories or small categories. The arrows in this category are functors from one category to another category. And you have a natural notion of composition of functors, etc., etc. You have an identity functor. And this identity functor satisfies the identity axioms for in the definition of a category, and you have associativity of composition. So it's so this category is indeed a category, and this notion of a category of all categories or all small categories is very much well defined. Now this category also has a further structure. It is not just a category, but there is something more that is associated to it. If you observe, if you just fix two objects in this category, that is, if you just look at two particular categories which are objects in this category, let's say C and D, and if you look at all the functors from C to D, then you know that there is a notion of a natural transformation from one functor to another functor, which mimics the notion of a map, right? So if you fix two categories C and D, and if you consider a new category whose objects are the functors from C to D, and whose morphisms or whose arrows are natural transformations from one such functor to another such functor, then this also forms a category in its own right. So what we are doing essentially is, we are fixing a category C, we are fixing a category D, and we are looking at the category of all functors from C to D. So you are looking at all functors which go from C to D. The objects in this category are these functors, and the arrows in this category are the natural transformations between such functors from one functor to another functor. And this again, you know that there is a way of composing natural transformations. You have identity natural transformation for every object, that is for every functor. So this indeed forms a category, and this is something called a functor category. It is called the functor category from C to D. Okay, so if we look at the category cat of all categories or small categories, then, and if you fix any two objects in this category, let's say C and D, then the collection of all arrows from C to D, that is the Hom set from C to D, is not just a collection, it is something more than just a collection. Namely, it is a category in its own right. Okay, and this category structure on each, I mean locally you have this category structure, that is you have a category structure for each Hom set, right? And this category structure is well behaved in a certain way, which I am not making precise at this point, but this is very well behaved with the composition of functors. Okay, with the composition of arrows in cat. So this is not, so the category of all categories is not just a category, it is something called a two category. Okay, why a two category? Because you have two different levels of arrows here. Okay, so firstly you have objects here, and you have arrows from one object to another object, and you then have arrows between parallel arrows, that is you from one, so let's denote this new kind of arrow by a fat arrow. So you have arrows, so you have the notion of an arrow from one arrow to another arrow as well. So this I mean the arrows between objects will be called as one cells, and this fat arrows will be called two cells. So this is called something called a two category. And in a similar way, you can also talk about n categories. You can even talk about something called infinity categories, which is a great area of research. I mean, there are loads of problems in this area, and yeah, and it's very fun to deal with. So anyway, so this is sort of the philosophy behind defining natural transformations. We wanted to define natural transformations because we wanted to understand maps between functors. It is precisely a map between functors. A natural transformation is precisely a map between functors. So a natural transformation is precisely a map from one functor to another functor. Okay, so with this sort of remark in mind, let us move on. Let us sort of try solving problems. Okay, so let us read out the first question. So we assume that R is a ring, and we know that R mod denotes the category of R modules, and since I didn't mention or say that R is a commutative ring, oops, sorry, just a minute. Sorry for the interruption. Yeah, so since I didn't mention here that R is a commutative ring, so by R mod I'll mean the category of left R modules. Okay. Now, question is asking that you have the category of left R modules, and you look at the identity functor from R mod to R mod. We need to show that this is naturally isomorphic to the Hom functor, which is represented by the ring R considered as a module over itself. Now, what is naturally isomorphic? You guys already know what natural transformations are, right? You know that if F and G are functors, you know the notion of a natural transformation from F to G, right? Now, as I mentioned that suppose, so F and G, in order to talk about a natural transformation, you need to have that the functors should have the same domain and the functors should have the same codomain. That is, the two functors should be parallel functors. So F and G are functors from C to D, right? And we know that we have the notion of a category. We have the notion of the functor category from C to D, right? The arrows in this category are natural transformations. Okay. So accordingly, once we have a category, we can also ask what are the which of the arrows are, that is, which of the morphisms are isomorphisms in this category. So those natural transformations which are actually isomorphisms in this category, they are also known as natural isomorphisms. Okay. And two functors between which a natural isomorphism exists the functors are said to be naturally isomorphic. Now, an equivalent way of understanding or an equivalent criteria for a natural transformation to be a natural isomorphism is that each component of the natural transformation should be each component of the natural transformation should be an isomorphism. So maybe this is a good exercise that we need to pin down. So we'll solve this one first and then we'll get to this question. So maybe I'll put some space here. So this comes down. So so this is our first question rather. A natural transformation alpha from a functor f into a functor g, where f and g are functors, parallel functors from a category script C to a category script D. A natural transformation alpha from F to G is a natural isomorphism if and only if. When does this happen? This will happen if and only if each component of alpha is an isomorphism. So maybe as a question I put true and false, true or false. So option A is true and option B is false. Okay. So we need loads of space now. Okay, so this is, as I mentioned, as I said, this is correct indeed. Now, by the way, what do I mean by the component, by a component of the natural transformation? So as you know, what is a natural transformation? A natural transformation alpha from F into G, as you know, is a map that assigns, it is a alpha from F to G, or from alpha, a natural transformation alpha from a functor F to a functor G is a map that assigns to each object of your domain category, which is C in this case, that assigns to each object of, let's say each object C. So we'll put a symbol, we'll take a symbol here that assigns to each object C of the category C, of the first category of the domain category C. It assigns to each object C of C a morphism. So a natural transformation alpha from F to G is a map. So a natural transformation alpha from a functor F into a functor G is a map that assigns to each object C of the first category C, of the domain category C, a unique morphism alpha at C, right, from FC into GC of the category D, right, such that this assignment is not arbitrary. This assignment is, this assignment of a morphism to each object of the first category, this assignment is natural in the object C belonging to the first category. What do I mean by this? Is that alpha at C is defined in a uniform way for all objects C in the first category. It is not defined, there are no arbitrary choices for alpha C. Okay, alpha at C is defined in a uniformly across, is defined uniformly across all objects C in the first category. So such that for every morphism F from C to C prime in the first category, which is C in this case, this particular naturality square commutes, this particular diagram commutes in D. So what is the diagram? So you have FC to GC you have this map alpha at C, the component of alpha at C, which is from FC to GC. Then you have the component of alpha at C prime, which is from FC prime to GC prime, denoted by alpha at C prime. And these vertical arrows coming downwards are basically the images of f under the two functors, ff and gf. So you have this query and you want this square to come in. Okay, for any morphism f, this square should come in. And what this basically, what this axiom, naturality axiom basically says is that the morphisms alpha c, as c varies over all objects in the first category, these morphisms are defined uniformly across all objects of the first category. Okay, that is, they are defined in the same way for all objects c in the first category. So we'll see a more concrete example of this to understand the naturality axiom. I hope you have already seen this previously, but we will see it. We'll see some examples now to understand it better. So yeah, so now we can so this is the definition of a natural transformation. A natural transformation is just a map that assigns to every object of the first category a unique morphism of the second category. Okay, so now we want to show that a natural transformation is a natural isomorphism. So by a natural isomorphism, as I said, what this means is that this morphism be an isomorphism in the functor category from C to D, or in other words, for this natural transformation there should exist a natural transformation in the opposite direction, such that the two compositions that you get are precisely the identity natural transformations on f and g respectively. So let us solve this. So solution: assume first that alpha from f into g is an isomorphism or is a natural isomorphism. Everything will work. So okay, so yeah, there exists, by definition there exists a natural transformation let's say alpha inverse from G into F, such that the composites alpha inverse, this composition alpha composed with alpha inverse is equal to the identity natural transformation, which I will denote by 1 on G, one of the object G in the functor category, that is one of the functor G, and alpha inverse composed with alpha is equal to the identity natural transformation on the object F. Now we know precisely how our natural transformations compose, and therefore thus for every object C in the first category, so for every object C in script C in the first category, alpha so if you look at the component of alpha at C, and if you look at the component of alpha inverse at C, so alpha inverse alpha, this is a natural transformation whose component at C is equal to the component of 1f at C, and you know that alpha inverse alpha, the component of alpha at C, sorry, just a minute. Oma, etu pokai ke niye jao na? Are pokai ke etu niye jao? Yeah, sorry for the interruption again. Yeah, so thus for every object C in the category C, alpha inverse alpha at C is 1f at C, and what is alpha, what is the component of the composition alpha inverse alpha at the object C? The component of this natural transformation is the composition of the components of alpha inverse at C and alpha at C, component of alpha at C. This is equal to what is the component of the natural of the identity natural transformation on F at C? This is precisely 1 at FC, right? And which implies, so we have this, we have alpha C composed with alpha C inverse is 1 FC, and similarly we also have, if we use the other identity, alpha at C composed with alpha inverse at C is 1 at GC, which implies that the component of alpha at C, which is a morphism from FC into GC, this arrow, this morphism from FC into GC is an isomorphism because it has an inverse. This morphism has an inverse, okay, and and this is true for all objects C. So each component of the natural transformation is actually an isomorphism, okay. Now we just need to prove the converse direction. So this is an isomorphism. Let me write the entire stuff. This is an isomorphism for all C, for all objects C in the first category C. Now we assume the converse, that is, we assume that each component of the natural transformation alpha, each component of the natural transformation alpha is an isomorphism. We just need to show that alpha is a natural isomorphism. Okay. So I need more space, maybe, yeah. Maybe not this much space, but yeah, I think this would do. Okay, so conversely, assume that for all objects C in the category C, the component of alpha at C, that is alpha C from FC into GC, is an isomorphism. So this means there exists a map, it's denoted by a different letter, beta C. We don't yet know what beta is, but we just denote the map by beta C, which denotes the inverse of alpha C. So beta C from GC into FC such that beta C is an inverse. Beta C is equal to alpha C inverse. It is the inverse of alpha C. So the interesting thing here is we'll now define a natural transformation, and as you can already understand, we'll define the natural transformation from G to F by patching up all these beta C's, right? So the interesting thing here is that even though we have a collection of arrows or morphisms from morphisms, we still, I mean, there is no way to be sure whether these morphisms all patch up together to give a natural transformation or not, right? But the interesting thing here is, since beta C is a pointwise or object-wise inverse for alpha C, and since alpha is a natural transformation, that is, the collection alpha C is a natural family of morphisms, or something called a compatible family of morphisms, or is defined in a natural way. Hence, all these beta C's have to be defined in a natural way. Okay, that is, these two, all these together will form, I mean, this collection of beta C's considered as a map will form a natural transformation. So the naturality is sort of imposed by the fact that alpha is a natural transformation. This is what we want to prove now. So we define a natural transformation. I shouldn't say natural transformation yet, as of yet, we haven't checked that. So define a beta from G into F by beta C, beta at any object C in our category, Okay, I should have used a different symbol maybe. All right, there's no issue with that. Maybe, yeah, I'll just write it as alpha c inverse. So by beta at c is equal to alpha c inverse for all objects c in script c. Okay, so what we did here is we defined an assignment which is the data of a natural transformation. That assignment to each object of the first category a unique morphism of the second category. So we assigned an object assigned to yeah, so an assignment to each object of the first category a unique morphism of the second category. So this is what we did. We assigned to each object c in the first category a morphism, namely alpha at c inverse, which is a morphism in the second category from gc into fc. Okay, what we just need to check, so this is the data of the natural transformation. What we just need to check is that whether this satisfies the naturality axiom or not. Okay, so it only remains to show that beta is a natural transformation, satisfies naturality axiom. Okay, so so yeah, so for this we just need to see this, that so let f mapping c into c prime be any morphism b, or maybe we'll just write a and b. That would be a better that would look better. So let f mapping a into b be a morphism, any morphism in the first category c. Okay, we just need to check whether that square commutes or not. Need to show that this particular square yeah, so the maps are from, yeah, so GA to GB, so GA to FA, GA to FA you have beta A, GB, GB to GB to FB, you have beta at B, and you have GF, and you have FF, right? We just need to check whether this square will commute or not for all such arrows F in the first category. That is whether this collection is a natural family. This collection of arrows beta C indexed by the object C in the first category, this collection of arrows in the second category, or this collection of morphisms in the second category indexed by the objects of the first category, whether this collection is a natural family or not. Yeah, so I need space, more space. Yeah, so we need to show that this commutes. Okay, so how are we going to show this, that this particular square will commute? Since alpha is a natural transformation, hence the naturality of alpha says that for the morphism f from a to b, hence fa to fb, fa to ga, fa to FB, FB to GB, GA to GB. So this is GF, this is FF, this is alpha at A, this is alpha at B. This commutes, hence this commutes. So Yeah, loads of space I need. So I'll just need more space. Let's see, do we have enough? Yeah. Hence this diagram, this square commutes, this diagram commutes. Okay, and if we just realize that this, we can just invert this arrow. This is the blue arrow in the opposite direction from GA to FA is just alpha at A inverse, and we can invert this arrow. This is just alpha at B inverse, and this blue arrow is alpha at A inverse. Okay, so since the original square commutes using the red horizontal arrows, since that original square commutes, hence this new square will also commute, which consists of only the red vertical arrows coming down and the blue blue horizontal arrows going in the opposite direction as that of alpha. So this will commute. Hence this square commutes. So that the square with the blue arrows, maybe it's best not to write them as dotted arrows, because dotted arrows denote existence of an arrow. I'll write solid arrows but in blue color in the opposite direction as that of alpha. Right, yeah, this looks better with the blue arrows commutes. Hence beta, which is defined to be the collection beta C from FC into GC. You can either think of a natural transformation as a map which assigns to an object of the first category a unique morphism of the second category, or you can think of it as a collection of morphisms in the second category indexed by the objects of the first category, such that you have the naturality axiom. So this collection of this map beta, where C is in OBC, right, this collection is a natural transformation. Oops, this is from GC to FC, is a natural transformation from G to F in the opposite direction as that of alpha, such that this is an inverse of alpha. And this we know is the case easily because component wise it's an inverse, so it will be an inverse by definition of composition of natural transformation, such that beta is equal to alpha inverse, and then we are done. Thus alpha is a natural isomorphism. Okay. Okay, so yeah, so this finishes the problem. Now we can move on to solving the next one. Now I can move on to solve the next problem. Okay, so I need to make space here. Okay, so again we read the first question, I mean the second question I should say. So yeah, anyway, that is not important here. So the question is saying that we fix a ring R which is not necessarily commutative, and we look at the category of all left R modules, and we and we uh, consider the identity functor from R mod to R mod. We need to show that this is naturally isomorphic to the Hom functor represented by R. So just a remark. So if you I mean, so a functor, any functor, so suppose C is a category, any functor from C into the category of sets, okay, which is naturally isomorphic to some Hom functor, that is Hom functor, covariant Hom functor represented by some object A in the category A, let's say. So any functor which is naturally isomorphic to a Hom functor is called a representable functor. Okay, so what this question is asking is to just show that the identity functor from R mod to R mod is a representable functor which is represented by the ring R considered as a left module over itself. Okay, so maybe I'll add this remark, that is, show that the identity functor from R mod from R mod to itself is represented. It's a representable functor that is represented by R belonging to OB R mod. This is just a small point of terminology, but very important, because representable functors are very important in category theory. These were first given by Grothendieck, observed by Grothendieck, and they are very important. And loads of functors are actually representable. And once you know that some functor is representable, you actually know a bunch of properties of such functors, bunch of category theoretic properties of such functors. I'll put category theoretic in quotes for the time being. What category theoretic property means, we'll keep all that in quotes. Anyway, so we just need to show that the identity functor is represented by this object R. That is, identity functor is naturally isomorphic to Hom R. Okay, so that is, we need to first of all define a natural transformation, which we then need to show is a natural isomorphism. So define a natural transformation eta from yeah, so define a natural transformation alpha so yeah, so define a natural transformation alpha from the identity functor on one R mod, I'll denote it like this, into the functor, or maybe in the opposite direction, that would be a better one, alpha from Hom R mod R comma bar into 1 on R mod by, so this is a natural transformation, so it will assign to every object of the first category, which is R mod in this case, a unique morphism of the second category, which is again R mod. So alpha at any object M should be a map from Hom R mod R comma M into M, right? And what is this map? This map sends any F, which is a mapping of R into M. It's an element in the Hom set from R to M, right? It's an element in the Hom set from R to M, and any element in the Hom set from R to M, as we know, is just an arrow in the category from R to M, or a morphism in the category from R to M, right? So an element is just a morphism from R to M. So we take any such map F from R to M, and this F is mapped onto F of 1. which is an element of M, right? So this now I leave for you to check that, or maybe we will do this. It's better that we do this exercise. Okay. So first of all, we need to see that this is actually an isomorphism in the category of all R modules. Okay. So what we need to see is that this is, since it's an isomorphism in the category of R modules, that means we need to check that this map alpha at M is both injective and surjective. Okay. Alpha at M is injective as at M is injective as um, so this is true because if you have two maps from R to M, to R linear mappings of R into M which agree on one, then the maps have to agree, right? So alpha at M is injective as alpha as for all f comma g in the Hom set from R to M, alpha at M of f is equal to alpha at M of g implies f of 1 is equal to g of 1, which therefore, sorry, I am not audible. Hello, can you hear me? Can you hear me? Can you hear me? Hello. I think it's a problem at your end because last week also there was a student, but she was able to hear. Maybe you can try to rejoin. Yeah, can you hear me?
Yes, sir. Yes, sir.
Yeah. Yeah. So f of 1 is equal to g of 1, and using R linearity this will imply f is equal to g. So I'll just put things in the bracket. This is very easy using R linearity of the maps. And how do you check that this map is surjective? Again, very easy, because you already know what free R module is, and R considered as a left module over itself is again free. The singleton set 1 is a basis for this R module. It's a free R module. So any free R module for that matter is actually a direct sum of copies of R. R itself is a direct sum of copies of R, and that is why R is a free R module. So yeah, so alpha at M is surjective as for any element M in M, uh, the set map which sends 1 to, I mean, the set map from 1 to M sending 1 onto M extends uniquely to an a linear map from R into M. Okay, so what this basically says is that the map alpha m, which we have defined here, is actually an isomorphism in the category of R modules. So note that even before we check that alpha m is an isomorphism for each object m in the category R mod, even before that we actually need to check that this alpha m's actually are natural, they are defined naturally. That is, this alpha so defined here as indicated is a natural transformation, and then we can check for whether it's a natural isomorphism or not. But we can do that simultaneously as well. We indeed have obtained that each component of alpha is an isomorphism. Okay, and finally for naturality. Okay, so finally we check for naturality. Okay, so as I already mentioned, I am a category theorist by training. I mean, my research involves in category theory. So these are the right kind of questions I believe are I mean, questions to be solved before for a first coursing, for a first time exposure in category theory. So finally we just check for naturality and then we are done. So let f from m into n be an R linear map, be an arrow in the category of R modules, be an arrow in R mod. We just need to check whether that particular square that we obtain out of this is a commutative square or not. So what is the square that we have? So alpha so defined here is from the Hom functor into the identity functor, right? So the square is like this: Hom R mod m r comma m to m. We have this map which is alpha at m. This arrow, this morphism has been assigned, which is alpha at m, and Hom R mod r comma n, this arrow into n, and we have this arrow f. I mean, sorry, this is not f, this is f star. As you know, for any f in the in your category, if you apply a Hom functor to that, we denote the corresponding. I mean, if we apply the covariant Hom functor, we denote the corresponding morphism at the level of, in the category of sets. That is, the image morphism in the category of sets is denoted by f lower star, right? Which is just post composition by f. So so just to be very precise, how does this operate? So f star is a mapping of Hom R mod r comma m into Hom R mod r comma m. If you take any element g, which is a morphism of r into m, right? You know that this is your Hom set. Hom R mod r comma m is your Hom set from R to m. An element g in this Hom set is by definition, I mean, we define an element in this Hom set to be a morphism of the object R into the object M, a morphism of R into M, right? So right, morphism of R into M. And how does f star act on this element? So the resulting element is f compose g, which is now a morphism R to n, right? It's a morphism of R into n, this composition. So this is how f star operates. And on the other side, you have this, you have applied the identity functor on f, so you just get f, right? And this is alpha at n. We just need to make sure that this particular square commutes, is a commutative square or not. Okay, that is whether f composed with alpha m is equal to alpha n composed with f star. So how do you check for this? So you take any element, let's say g here, right? And alpha m applied on g, as we already know, is g of 1. This is f of g of 1. On the other hand, if you take f star, apply f star on g, then you get f compose g. And alpha n, as it was defined, this is equal to f composed with g of 1, right? But we know by definition of composition of mappings, f composed g at 1 is f of g of 1. So they agree, and this is true for all g, which shows that this particular square is a commutative square. Right? And therefore you do have a natural transformation. Let me make some space. Yeah, so you indeed have a natural transformation. So thus alpha mapping home r mod r comma bar into uh, 1 r mod, that is identity functor on the category r mod, is a natural transformation. We have checked for naturality. This is a natural transformation. We have checked for naturality. Alpha assigns, that is alpha assigns to each object of your first category a morphism in your second category. Okay, alpha is a natural transformation. And we also have checked at the beginning that each component of the natural transformation alpha is an isomorphism, right? That is each alpha m, as m varies in over all the modules in your over all the objects of your category, each alpha m is an isomorphism. This is what we have checked this at the beginning. So this is not just a natural transformation, it is also which is in fact, which is a better word would be in fact, which is in fact a natural isomorphism. Okay, and then we are done. So what we have basically shown is that the identity functor from r mod to r mod is naturally isomorphic to the Hom functor represented by r. That is, the identity functor is a representable functor. Okay. Okay, so yeah, so in case you have any questions, you can always email me, that I keep saying every week. Please do write to me if you have any questions regarding the material that is being covered. And my email ID, as you can see here, is this. Yeah, so let's move on to the next problem. Okay, so let me make some more space. I need so much space today. Yeah. Maybe we'll skip the last problem in case we don't have time. This one is, yeah, very easy. So let's read out the problem first. It says that we have to prove that if a functor f from a category A into a category B is fully faithful, then for any two objects x and y in your domain category, if the images fx and fy are isomorphic, then the objects have to be isomorphic. Okay, that is, if the image objects so you have a functor f from A to B, it takes objects to objects and it takes arrows to arrows. You are given that for some objects x and y in your domain category, if the image objects of x and y under f respective f of x and y respectively under f, that is the objects fx and fy in the category B are isomorphic, then the original objects x and y have to be isomorphic as well. So just to be very just to be very what should I say, very precise, let me first of all define what fully faithful functor means. So maybe I'll write this in blue. So recall, I don't know if it has been defined by in the classes, but we define a functor f of a category script A into a category script B. So a functor f, so a functor Yeah. Yeah, functor f of a category A into a category B uh, is number one faithful if the functor is locally injective. That is, if for so you know if f is a functor from A into B, then for each pair of objects A and A prime in your domain category, you have a mapping, right, of the Hom set A from A to A prime into the Hom set from FA into FA prime, right? This is one of the this mapping of a script A comma A prime into script B FA comma FA prime is part of the data of a functor, right? It is in fact part of the arrow function of a functor. Okay, so you have this mapping of script A comma A prime into script B FA comma FA prime, right? There's no issue with that. This is how a functor was defined, right? For so named what is a functor? It's a mapping of one category into another category. A functor from A into B is a mapping of A into B. So whatever data is present in the category A, you have to map it into the category B. Keeping in mind, the functor should preserve the structure of the category, which means that it should map objects to objects. So if A is an object in A, in script A, then f of A will be an object in script B, right? That is a functor will map objects onto objects. It will map morphisms onto morphisms, right? And this is what this mapping says. For each pair of objects A and A prime in the first category, you obviously have the Hom set from A to A prime, and this collection of arrows from A to A prime in the first category should be mapped onto this collection should be mapped into the collection of arrows from FA into FA prime in the second category, right? This is part of the data of a functor. So an arrow in this set, let's call it F, an arrow in this set from A to A prime should be mapped onto an arrow in the second category B. So let's say this gets mapped onto this arrow, which is f of f applied on f, which is an arrow from FA into FA prime. Okay, so arrows will get mapped onto arrows. The functor will assign to every arrow in your first category a unique arrow in the second category, right? This is what a functor does, right? So you have this mapping for each pair of objects A prime in the first category. You have this mapping of the Hom set from A to A prime into the Hom set from FA into FA prime. Okay, this mapping, which sends f to f of f, this map is injective. So the functor is called faithful if for each pair of objects A comma A prime, this mapping at the level of Hom sets, this local map is injective for each pair of objects A comma A prime. So it is called full if for each pair of objects in the first category, the mapping, which is part of the data of the functor, this into this mapping again, the same mapping which sends f to f of f, right? So earlier for faithfulness you demanded that this mapping be an injective map. Now if you want, for the functor to be a full functor, we demand that this particular map should be surjective. Okay, that is, the functor should be surjective at the level of Hom sets. It should be something called locally surjective. Okay, that is the mapping of the Hom set from A to A prime into the Hom set from FA to FA prime. This mapping associated to the functor should be surjective for each pair of objects A comma A prime in the domain category. And so we have defined faithful, we have defined full. So what is fully faithful? A functor which is both full as well as faithful, which means that for each pair of objects A comma A prime in the first category, this mapping that you have of the Hom set from A to A prime into the Hom set from FA into FA prime, this mapping should be bijective, both injective and surjective. All these mappings, as you vary the objects A prime in the first category, the mappings that you get, these mappings should be bijective. That is what fully faithful means. So a functor which is both full and faithful is called fully faithful. So yeah, I need space. Maybe I'll just push things pretty down. uh, I think this would do now. Yeah, so 3, fully faithful if the functor f is full and faithful. That is the mapping that is for each a comma a prime in the first category, in that is in script a, the mapping as associated to the functor, the mapping from script a comma a prime into script b f a comma f a prime should be a bijective mapping. Then the functor f is fully faithful. Okay, now let's look at this exercise. So it says that for a functor f from a into b, which is fully faithful, if for objects xy in the first category fx is isomorphic to fy, the objects fx and fy in the category b are isomorphic, would imply that the objects x and y in the category a are also isomorphic. So, and a very characteristic property of functors that we always have or use throughout mathematics, wherever, let's say in topology, in algebra, wherever we have a functor, we always try to use this property that a functor preserves isomorphism. That is, it carries isomorphisms onto isomorphisms. You already know that functors map morphisms onto morphisms, and using the property, using the functoriality of a functor, using the axioms in the definition of a functor, you can actually prove that it in fact maps isomorphisms to isomorphisms. That is, if a morphism is invertible, then its image morphism will also be invertible. This is a property of a functor. So if f is a functor from a into b, you can show that for objects xy in the category a, x is isomorphic to y will imply that the image objects fx and fy are isomorphic. But the question here is asking something in the converse direction. It says that if the image objects are isomorphic, then so are the starting objects. Okay, so what I'm trying to say here is this, you have an implication in the opposite direction as well. You have something in the opposite direction as well, but this is very trivial. This is true for every functor. What is interesting here is that the functor has been assumed to be fully faithful, and then you can show that if fx is isomorphic to fy, then x has to be isomorphic to y. Okay, so I mean just a bit of remark here. So one of I mean a very essential problem throughout all of mathematics is something called classification problem. So whenever you study a new kind of mathematical objects, let's say you studied groups, you studied rings, you know what topological spaces are, you know what metric spaces are, etc., etc. So an interesting so the classification problem is all about classifying objects. Okay, so you just need to you are always searching for ways to find out whether two objects are isomorphic or not. You are given two groups, you want to find out whether these two groups are isomorphic or not. You are given two topological spaces, you want to find out whether these two topological spaces are isomorphic or not, that is homeomorphic or not. And the most interesting way to do this is by constructing functors from one category to another category. So for instance, suppose you have a functor from the category of topological spaces into let's say the category of groups. Okay, you know that a functor by default, as I mentioned, a functor by default always preserves isomorphisms. Okay, so if you know that two topological spaces are isomorphic, that is homeomorphic, then the corresponding image objects, which are groups now under the functor, these corresponding image objects will have to be isomorphic, right? So if f is a functor from top to grp, from topological spaces to groups, if f is your functor, and if spaces x and y are isomorphic, then the groups fx and fy will have to be isomorphic. So you can use this particular property in the contrapositive direction as well, and this is very interesting. And what you can do now is you want to use contrapositivity. So you start with spaces x and y, you form their algebraic images, you apply the functor to them, you obtain the corresponding objects in the algebraic category of groups fx and fy. If these two are not isomorphic, then the original spaces won't be isomorphic, that is homeomorphic, right? So this is a very powerful idea that is used all throughout mathematics. But the place where mathematics sort of fails here is that The functors, while they preserve isomorphisms, don't generally reflect isomorphisms. Okay, so what do I mean by reflecting isomorphisms? So reflecting isomorphism means that suppose f is a functor from a into b, then the functor f will reflect isomorphisms if for every morphism f in your domain category, that is in the category a, whenever f of f is an isomorphism, then f will also be an isomorphism. Okay, that is functors by definition map functors by definition map morphisms onto morphisms, right? They carry arrows to arrows. Now functors preserve isomorphisms, they map isomorphisms in particular to isomorphisms, but it could happen that for a functor f you take a morphism which is not an isomorphism but the image is an isomorphism, right? Now a functor reflects isomorphisms if this situation doesn't happen. That is, whatever isomorphisms you obtain as images are actually coming as are actually images of isomorphisms, not just arbitrary morphisms. Okay, that is, whenever f applied on some little f is an isomorphism, then little f has to be an isomorphism. Okay, the starting morphism will be an isomorphism in that case. So this problem is very easy, even though I spoke a lot here, but this is very easy if you have understood the definitions properly. It says that a fully faithful functor reflects isomorphisms. It is saying, it is asking to prove something weaker, but will in fact prove that it reflects isomorphisms. So now let x be now let x and y be objects in your first category A, and let fx be isomorphic to fy. Okay, what do I mean when I say that fx and fy are isomorphic? This means that there is a morphism of fx into fy which is an isomorphism. So then by definition there exists a morphism, there exists an isomorphism, you can say it directly. Morphism if there is an isomorphism from fx into fy, let's call it f. This is an isomorphism, so I'll put a tilde at the beneath the arrow. Yeah, so this is an isomorphism, means that this has an inverse. It's an invertible morphism, it has an inverse. Let's call the inverse g. Let g be its inverse. Now since the functor f is full, hence the associated mapping at the level of Hom sets for the ordered pair of objects x, y, that is this map from script A x, y into script B fx comma fy, which sends any f to f of f, this map. Okay, so full plus faithful, I'll just say, I'll use everything all at once. This map is bijective, right, which implies there exists f prime from x into y such that f applied on f prime is equal to f, is equal to the morphism f. And similarly, if you apply if you use the fact that the corresponding map from for the ordered pair y comma x, that is the mapping of script A y comma x into script B fy comma fx associated to the functor, this mapping is bijective if you use, precisely because f is given to be fully faithful, right? Since it's fully faithful, for each pair of objects in the first category, the associated mapping at the level of Hom sets will be bijective, right? Because it's fully faithful. So in particular the mapping from script A y comma x into script B fy comma fx will again be bijective. So similarly there exists a g prime from y into x such that capital sorry, such that f of g prime is equal to g. Now you know that little f and little g are inverses of each other. That is what we assumed. So g composed f. Okay, so one. So what is my domain of codomain of f? Yeah, fy. So g composed f is from one. Yeah. So the identity morphism on the object fx, which is equal to g composed f, which is equal to f of g prime composed with f of f prime, is equal to f of g prime composed f prime. This is just the one of the axioms of a functor, of any functor. Okay, so f applied on g prime composed f prime is equal to 1 applied on fx, right? And 1 applied on fx is just capital F applied on 1x, right? So g prime composed with f prime is a morphism from x to x, such that the functor f applied to this morphism is equal to the functor f applied to the morphism 1x. Again, if you just use the faithfulness of the functor, that is for the ordered pair x comma x of objects in your first category A, you know that this map from script A x comma x into script B fx comma fx, which sends f to f applied on f, the mapping associated to the functor for the ordered pair x comma x, this map, you know, since the functor f is fully faithful, you know in particular this map is bijective, and you have already obtained two different elements in this category, g prime compose f prime, I mean two different elements in this set, g prime compose f prime and 1x, both of which map to the same element, right, which is 1 at fx. Since the map is bijective, in particular injective, this mapping is bijective, in particular injective, hence g prime composed f prime has to be equal to 1x, right? That is, as you know, injective maps by definition preserve distinctness of elements. So this will imply, so maybe I'll just write this implication, I mean the reason on the top, faithfulness of the functor f. This implies that g prime composed with f prime is equal to 1 at x. And similarly, if you consider the local mapping associated to the functor, the mapping for the ordered pair y comma y, right? Similarly, you get f prime composed with g prime is equal to 1y. Okay, thus f prime is an isomorphism. And what was f prime a map from what to what? I mean, what was the domain and the codomain of f prime? So f prime was a morphism of the object x into the object y, right? It was a morphism of x into y. And since f prime is an isomorphism, hence x is isomorphic to y, and that is what we needed to prove, right? But we actually proved something more, that is that is a fully faithful functor actually reflects isomorphisms. Okay, this functor actually reflects isomorphisms. That is, whenever you have a morphism f in the first category script A, in your domain category script A, if you apply the functor f on this morphism, and then accordingly if you apply a functor f on any morphism, you will arrive at a morphism in your codomain category, that is, you will arrive at a morphism in script B. So you start with a morphism f in the category script A. If you apply the functor capital F on f, you have a morphism in script B. Now if this morphism is an isomorphism in script B, then the original morphism that you started with, that is the morphism little f in the category script A, is an isomorphism. A fully faithful functor will always reflect isomorphisms. So this is a completely category theoretic proof. There was, I mean, of course it has to, because it was a question in category theory, but yeah. So again, if you have any questions, you can ask me. So whoever is attending this right now, any questions you can ask me, or for those who will be seeing the video, you can always write to me. So which week are you currently in? I mean, what is the course currently? What is the week going on? It's week 7 or week 8? Am I audible? Am I audible? Yeah, so what is the current week going on? Week number? Because the tutorials have sort of started a week 2 weeks later after the lectures, and I know that this is the last week you'll be studying category theory, because it was supposed to be for 2 weeks. But what I'm asking is, what particular week number is this are you currently in? For the tutorial it is week 8, I think. Let me just check once again. Yeah, but yeah, so probably you are in week 9 maybe. I might be wrong. Okay, so maybe we'll skip question 5 and question 6, uh, but we definitely have to solve up to 4. Yeah, let me make some space. Is this enough space? Okay, so let us read this question again. Not difficult, but yeah, there's a reason I'm doing this, precisely because of the second part of this question. It's very important. But let's first talk about the first part. So we basically want to give examples of the following. Okay, first of all, we want to give an example of a functor from the category of rings to the category of groups. Okay, now there are various functors from rings to groups, but there are two particular functors that we are interested in right now, which will actually allow us to, or help us to solve the next question. I'll just mention one of the two functors, and I'll leave it for you to check whether it's a functor or not. I'll just mention the assignment. That is what it does. I will mention the action of the functor. So we need to give an example of functor from ring to group. So this is how I define my functor. So we define this functor. It's just a symbol from ring into GRP. What does it do? This functor maps any ring R into the group of units of R. Okay, by the way, whenever I say ring, I always understand that this is the category of unital rings, that is rings with one, not necessarily commutative, but definitely unital. And the ring and the maps, that the arrows in this category from one object to another object are unital ring homomorphisms. That is, these are ring homomorphisms which also preserve or respect one. So this functor maps every ring to its group of units. It maps S also to its group of units. And how does it act on the arrows? To which arrow does it map an arrow? So you take an arrow in this category F and you map it onto the corresponding arrow F cross. Okay, what is F cross? F cross is just F restricted to R cross. You just restrict F to R cross. So first of all, why is this a well-defined association or assignment? Observe that if F is a ring homomorphism from R into S, so it in particular would carry 1 to 1. Now if little a is a unit in R, then F of A, its image under F, has to be a unit in S, right? Why? Because if A is a unit in R, then this means that AB is equal to BA is equal to 1, which would mean that FA times FB is equal to FB times FA, which is equal to F of 1, which is 1, right? So what I'm saying is, any ring homomorphism, any unital ring homomorphism will always carry a unit to a unit, right? And that is why if you take F to be a ring homomorphism of R into S, then F restricted to R cross will be actually a group homomorphism of R cross into S cross. There's no doubt about this. So this is my mapping. Okay, so this is my functor. I have defined what this functor does to objects and what it does to arrows, right? You just only need to check whether this is, I mean it will be, you just need to check that this satisfies the functor axioms. So the object function of the so just to be precise, the object function of the functor is this, and the arrow function of the functor is this. This is my arrow function and this is my object function. Just check that this satisfies, this functor preserves the categories, I mean this map preserves the category structure. This is a mapping. I have defined a mapping of the first category, that is the category of rings, into the second category, that is the category of groups. I have defined a mapping of rings into groups, and you just need to check that this mapping of the category of rings into the category of groups is actually a functor. It satisfies, it preserves composition and identities, to be very precise. So check that this is a functor. And I'll give one more example. And this I'll again leave for you to check. So define from ring into GRP. What does this do? This maps any ring R to GLNR. So I have fixed some n. Okay, so fix n in natural numbers. I hope that all of you know what GLNR means. GLNR is the general linear group, right? Is there an issue with non-commutative rings here? No, I don't think so. Yeah. So what is GLNR? GLNR is precisely the set of all invertible n cross n matrices with coefficients from the ring R, right? And this forms a group under matrix multiplication. Yes, general linear group, right? It maps S to GLNS, and it maps any ring morphism F onto the group morphism F hat, I would say, where F hat, sorry, I use the same symbol for the functor. You should have told me. This is not, this is a different functor. Why am I using the same symbol? I don't know. So define, let's say I'll use this symbol GLN bar. Okay, this is my functor now. So F will be mapped onto GLNF. Okay, what is GLNF? What is this GLNF? So where GLNF from GLNR, it should, whatever it is, it should be a, so it is an arrow, we know that much, we know, because this is a functor. It will map morphisms onto morphisms, that is arrows onto arrows, but we need to check that this is a group homomorphism. So GLNS, right? What does it do? It takes any matrix Aij here and it maps it onto F applied on Aij. You have the corresponding matrix, which is an n cross n square matrix over S. But what is important here to check the following is that this matrix, first of all, is invertible. You have to check that this is an element of GLNS, not just MNS, right? You have to check that this is invertible, and secondly you need to check that GLNF is a group homomorphism. Okay, and all of this will follow easily from the fact that F is a unital ring homomorphism. So check that GLNF is a group map. So check that GLNF is a group map, and check that, also check this, GLN bar is a functor. It's a functor of the category of rings into the category of all groups. Check that GLN bar is actually a functor from the category of all rings into the category of all groups. Okay. Yeah, so these are the two examples and that I wanted to mention for the first problem, and this is what we are now going to see. We'll precisely try to understand, you know what natural transformations are, as I have mentioned again and again. Those are maps between functors, right? Now we'll try to interpret the determinant of a matrix as a natural transformation. It might sound very bizarre and weird, but it actually is the case that determinant is a natural transformation. In what way, we'll see this soon. But before that, I want to know something. So we have solved problem part 1 of this problem. Tell me something, Ravi. Do you know what topological spaces are? Do you know what topological spaces are? Ravi, I am asking you. Because I'm not sure of the background here. Yeah, do you know what a topological space is? Okay, that's fantastic. Then we can talk about the second example as well. This will take a few minutes, but it's very important to know this. Some more space. So this is problem 2. We want to give an example of what? We want to give an example of a functor from the category of rings to the category of topological spaces. Okay. So define, this is very important. Okay. So even before we define the functor, so this is a fun exercise for you. Oops, what went wrong? I don't know. Yeah. So let R. Okay, so yeah, I need to make some changes here. This is not just ring, this is C ring, that is commutative rings. So I'm looking at the particular subcategory of commutative rings, okay, and ring homomorphisms. It's a full subcategory. So let R be a commutative ring. Okay. Now this is very interesting. For any subset E of R, so I'm defining a set, let V of E be the set of all prime ideals I'm skipping a lot of things. Take R to be a commutative ring, and you define a set spec of R, something called spec of R. We don't know what it is, but we define it to be the set of all prime ideals of R. All prime ideals you collect and you form spec of R. So what I want to do is, I want to make this set spec R, whose elements are prime ideals of R. I want to make this set into a topological space. Okay. So for any subset E of R, we define V of E to be all those prime ideals P of R containing E. You take any subset E of R and you define V of E to be the set of all prime ideals P which contain E. Okay. Now this is a very simple exercise that I am leaving for you to check. Check number one, V of E, V of the subset E is equal to V of the ideal generated by E, which is equal to V of the radical of the ideal generated by E. Number two is check that V of I mean check that the collection V the collection of all these sets VE is closed under arbitrary intersections. So intersection some index set I is V of union EI. And finally check this, that V of alpha union V of beta is equal to V of alpha beta, which is equal to V of alpha intersection beta for all ideals alpha comma beta of R, and this is for all sets EI contained in R where I is in some index set I, and this is for all sets E. So check that this collection VE of sets that you have obtained satisfies these three axioms, and if you look very carefully or closely, what the second axiom says that the collection of sets VE is actually closed under arbitrary intersections, and the third point says that this collection is closed under finite unions. Okay, and you can also prove that the empty set is of the form VE for some E in R, and the full spec R, the entire set spec R is also of the form V of E for some E in R. So what I'm trying to suggest here is that, so you have a set spec R which is a set of all prime ideals of the ring R, and you have obtained subsets of these sets, that is you have obtained VE, each V applied on E, each VE is a subset of spec R, right? And this collection of sets is closed under arbitrary intersections, finite unions, and contains the empty set as well as the entire space, entire spec R, right? So what this says is that this collection VE, so thus the collection VE such that E is in, E is a subset of R, or we can be very precise, and instead of VE we can say V alpha, where alpha is an ideal in R. It's the same thing as given by the first exercise. So alpha is an ideal in R. This collection is the collection of closed sets, right, for a topology. Closed sets for a topology on spec R. Okay. So what we have obtained is that you have obtained this collection V alpha satisfies the axioms for closed sets for a topology on spec R, right? Hence, if you take their complements in spec R, that will give you a topology on spec R. That is, these will be the open sets of spec R, right? Thus, spec R, comma V alpha, I don't know how to write it without making it ugly. Let me just say that the spec R is a topological space. Okay, and that the corresponding topology, which is obtained by taking complements of each of these V alphas, right? This topological space is called the Zariski space of the ring R. Okay, the topology is called the Zariski topology, and this topological space is called the Zariski spec for the ring Zariski space for the ring R, and it has very nice, interesting properties. It's compact, it's T0, etc. Many interesting topological properties. Okay, and this space, this spec R that we are talking about, is actually the starting point of algebraic geometry. In algebraic geometry, one starts from here and goes on, I mean, defines something called affine schemes, then schemes, etc., etc., and does a lot of interesting stuff. Okay, but the point is we actually have a functor now. Okay, so check that this spec, which is a mapping of C ring, commutative rings, into the category of topological spaces, which sends objects, that is rings, onto spec R, as we have defined here, onto the topological space spec R with its Zariski topology, S onto spec S, and any map. Yeah, I should sim. Yeah, and any ring homomorphism F onto this arrow F star. Okay, what does F, so note something in particular. Usually whenever we talk about a functor, we know that if F is a functor, and if you take a morphism from, let's say, morphism little f from A to B, then the image morphism, that is F applied on FF, will be a morphism from FA to FB, right? But here the functor reverses the direction of the arrows, right? So if F is a morphism from R into S, then F star is a morphism from spec S into spec R, right? That is why we don't actually have a functor from C ring to top. We actually have a contravariant functor from C ring to top. That is, we have a functor from the opposite category of commutative rings, that is C ring op. I should be precise and say C ring op, but let's not write it for the, it would only make things complicated. But yeah, so it's a contravariant functor from C ring to top. That is, it's a functor from C ring op into top. Okay, so this is spec, this is my spec. So check that spec from C ring into top is a functor. Okay, yeah, I need to define what F star is. So where F star maps spec S into spec R, it maps any prime ideal Q, which is a prime ideal in S, onto F inverse Q, which is a prime ideal in R, right? Check that this is a functor, is a contravariant functor. From C ring into top. Okay, so this is called the spec functor, and it's, as I mentioned, it's a very, very powerful functor. This construction is used throughout all over in algebraic geometry. Yeah, maybe I'll erase this problem. And we'll just talk about our last question and then we'll end. Okay, so finally we discussed this problem. We need to interpret the determinant of a matrix as a natural transformation. Okay, So a natural transformation has to be from one functor to another functor where the two functors are parallel functors. So even before we talk about the functors, we need to talk about the categories. So consider the functors. So we consider these two functors. One is, so we have ring on one hand, we have GRP on another hand, and we take these two functors. This is one functor and this is one functor. So the first functor is GLN bar, okay, and the second functor from ring to GRP is cross, okay. We have mentioned these functors just in the last exercise, okay. And what we now do is we define the natural transformation det from GLN bar into by, what does it do? It maps an object in your first category, which is a category of rings, onto a morphism in your second category. What is this morphism? So det at R, the component of this natural transformation det at the object R, which is a morphism from yeah, maybe it's better to write it like this. It's a morphism from GLNR. So det R from GLNR into from GLNR into GLNR into R cross, okay. This is just the usual determinant, okay. So what is this? This is just the usual determinant map, okay. So this is the data of my natural transformation. It associates to every object in my first category a morphism in my second category. So it associates to a natural transformation, by definition, as we know, associates or assigns to each object of the first category a unique morphism in the second category, such that you have the naturality axiom, okay. So check that. This is what I again leave for you to check, because we are almost out of time, but so right, yeah, so this is what my det is. Check that det from GLN bar into group of units functor is a natural transformation. So check that this is a morphism of functors, or a natural transformation from yeah, that is, check that this collection of arrows det R, as R varies over all objects of your first category, is actually a natural is a natural transformation, satisfies the naturality axiom. So what this essentially says is, if you think about it a bit logically, so what this says is that determinant, see, whenever you want computing the determinant of an n cross n matrix, you know you have a formula for that, right? Now this formula is independent of the ring, right? If you take a ring, if you take matrices over, let's say, rational numbers, you compute the determinant in the same way as you would do if you take matrices over, let's say, real numbers or complex numbers, right? So determinant has the same definition for all rings, right? That is, determinant is defined in the same way for all objects in the category of rings, right? You don't have you don't have one definition of determinant for one ring, another definition for another ring. You have the same definition, right? So this is what the naturality axiom says, right? That is, the components of a natural transformation are natural in the objects of, and I mean the component alpha c of a natural transformation alpha is natural in the object C belonging to the first category, means that the arrows alpha C, alpha at C, as C varies over all objects of the first category, are defined uniformly or in the same way, right? This is what it says, okay? So intuitively what it says is that, this is just a remark, naturality means that det R is defined in the same way. For all objects R. Ring. You don't have so you don't have different definitions of determinant for different rings, but the same definition. Right, this is what it says. Okay, so I'll just leave the last problem as a homework. So what this problem is saying is that, so if you recall quickly, then in the last week we did one exercise which says that every group can be thought of as a single object small groupoid. What is a groupoid? A groupoid is any category in which all the morphisms are isomorphisms, in which every morphism is invertible, that is, every morphism is an isomorphism. Okay, so a group can be thought of as a groupoid, that is a category in which every morphism is an isomorphism, such that this category has a single this groupoid has a single object. So a group can be thought of as a single object small groupoid. We just need to consider the functor category from the category G into the category set, right? That is a category of all functors from G to set, as we mentioned. The objects here are the functors from G to set, and the arrows in this category are precisely the natural transformations or morphisms of functors. Okay, so if we look at the functor category from G to set, we just need to show, or you just need to show, that this category is actually isomorphic to the category of all G sets, that is a category of all actions of G on sets, group actions, and the morphisms in this category will be obviously the G equivariant maps, right? So this is a homework problem, since we don't have much time left, but this is very easy. So homework problem, question 5, and a hint for this would be show that an object in this functor category, in the functor category from G to set, okay, show that a functor from G into set, let's call this functor f, a functor f of the category G into the category set is a set X. What is X? So observe that G is a category with a single object, right? So if f is a functor from G into set, f will assign to this single object of G some unique set, right, in the category of sets. So let's call this set X, right, together with an action of G on X. And where do we get this action from? So dot is, so the group G can be thought of as this category. It's a single object category with arrows as indicated here, morphisms. Now you have a functor from this to set. What does this functor do? This functor maps an object to some set X, okay. And what else does a functor have do? It maps arrows to arrows, right? So this functor will map arrows here in the first category. The arrows here are from dot to dot, so the image arrows will be from X to X, right? So it maps endomorphisms of dot into, so this is yeah, it maps this into endomorphisms of X, right? Now endomorphisms of dot are G precisely, and endomorphisms of X will be, so yeah, so since the endomorphisms here, endomorphisms of dot here are actually automorphisms of dot, right? Why? Because every element of a group is invertible. We saw this last time. So the endomorphisms are, all of them are isomorphisms. G is a groupoid, so every morphism is an isomorphism. So aught dot will be mapped onto aught of X actually, which is contained in end X. Why? Because so this is the object function and this is the arrow function, right, which maps F onto F. So why is the image actually contained in aught X? Do we normally know for a functor the image is contained in end of X, right? The image will be contained in end of X. If we have a morphism from dot to dot, then the image morphism will be a morphism in the second category from X to X, right? It will be an endomorphism of X. But since every morphism in the domain is an isomorphism and functors preserve isomorphisms, right? So this will be a mapping of aught of dot into aught of X. And this mapping that we have here of aught of dot into aught of X, that is of G into aught X, right, is actually what your action is, right? Of action of G on X, right? So this is your hint. Yeah, so with that in mind, I would like to stop this session, and please do look into this problem, try to solve it, see what natural transformations between two actions will be, or between two such functors from G into set will be. That is, what will be the arrows in the functor category whose objects are all functors from G to set. Okay, so we'll end the session here, and if you have any questions you can always email me, and thank you. So I'll stop the recording.